Hello everyone, my name is Tyler Kang and I'm a CAE consultant from Midas. Welcome to Midas's Elite Engineer webinar session. Today's webinar session will be on FEA model comparison and staged analysis for curved girder bridges by Tom Less. Our guest speaker for today, Mr. Less is a structural engineer and a team leader at Wolpert. He has finished his bachelor's and master's degree at The Ohio State University, and to briefly mention about his previous projects, he has worked on the CVG CONRAC elevated road structures and multiple projects with the Department of Transportation of Ohio. Mr. Less will give his presentation for the next 40 to 50 minutes, and he will use the remaining time to answer any questions that you have. And now I will pass the webinar over to Mr. Less. Thank you.
Okay, can everyone hear me and see my screen? Hopefully the answer is yes. All right, I will go ahead and get started, and hopefully that is the case. So we'll be talking about curved bridge analysis, so a couple comparison of different methods, and construction staging, which is becoming a more important topic for many of our structures. So a couple of things that we'll talk about is a traditional girder line analysis with V-load as a preliminary engineering method, a two-dimensional grillage analysis, and what I'm calling a grillage 2D plus or partial 3D, and then a full three-dimensional analysis. I'll give you a little bit of background on the CVG CONRAC project, and a couple of the models that we created are comparisons of those models, and then construction sequencing and constructability checks in those, as well as Guernsey 513, which is a NODOT project where we were using temporary supports with staged construction. So to give you a brief background, and I'll try to make this fairly accessible for those who may not have done curved structures in the past, but also hopefully give you some good information if you have done these. Girder line modeling is our traditional method. That's what we do in MDASH or other simplified programs. It's going to use an AASHTO live load distribution factor out of the AASHTO code to determine your live load distributions. Usually this can be done minimal time, not a complicated analysis, and it's the typical standard for straight bridges. In this case, we used MDASH, and then we used the V-load analysis as a spreadsheet. You could also do as a hand calculation to iterate and basically determine the amount of curvature effects we think we're going to have on the structure. And you can do this by taking a target, what I'll call utilization ratio, which is basically your demand over your capacity, and subtract off how much V-load increase you think you're going to have for the curvature effects in order to design your members in a preliminary design fashion. This typically does pretty good results for dead load approximation. However, for live load, it's a bit more variable, mainly because when you get into influence surfaces, there's a lot of intermittent sections within your influence surface that could be loaded and have some effect on the girder that you're working on. And that's hard to capture in the V-load. You can't really do that in a typical girder line and V-load analysis. So that's why we go to more advanced analysis. But this is typically used for preliminary engineering purposes. It's a good tool, and I definitely recommend it. And here's kind of the basic theory behind it. There's a lot of references out there. Again, it's a bit older method to do this by hand. You can also do it in spreadsheet. Basically, you're going to take the girder line and you're going to straighten the girder along the arc and design it basically as that arc length as a straight member. Then you'll take external loads and apply them to your structure to try to model the horizontal curvature effects. And that's what that figure down on the bottom right is showing. In past projects, this has worked fairly well for radii that are relatively large, over 1,000 feet or 1,200 feet. We typically aren't seeing a lot of difference between our line girder analysis with V-load, and our final finite element models. But if you get below that, you can start to see some larger differences. And in AASHTO 46224 there, that has limitations on when and when you can't use this. And most of the time, you're probably not going to be able to use this for your detailed design. At this point, we have enough tools through Midas or other programs to analyze these more appropriately. And the biggest thing is they may do fairly well for a moment, but it's going to underestimate deflections, twist, your differential reactions, that kind of thing. So we'll go into the grillage, otherwise known as two-dimensional, and there are a couple different things that are covered under this methodology. So I'm going to try to define these a little bit more, so as I go through this presentation, it's a little clearer what I'm talking about when I call something a grillage analysis or a 3D analysis. So in a typical grillage analysis, you're looking at either a single beam girder that has composite section properties or a beam and girder that has eccentric beam and an eccentric plate or frame element for your deck. So you're getting your full composite properties through an eccentric beam, and then you have full distribution of the live loads through an influence surface because you're creating a grid, which is why the grillage name came about. And that's going to allow you to do a much better distribution of your live loads, distribution of your superimposed dead loads. The question starts to become how much of your lateral stiffness is modeled within that grillage analysis. So is the deck stiffness accounted for? Is the cross frames accounted for? These are the questions that kind of determine, how detailed is your grillage model. So this may or may not include full lateral stiffness of the structure, but it would distribute the forces and distribute the loads from superimposed and live loads much more accurately. So what I'm calling this two-dimensional plus or limited 3D analysis is going to take that, and this would add in the cross frames or diaphragms and account for your full three-dimensional stiffness of the structure. Usually, again, you could do this through eccentric beam, but then you have additional linked nodes and linked elements that are going to model those cross frames in 3D and provide the actual stiffness laterally of the structure. So this is just like the previous one. You're going to get your full distribution of live loads, your full distribution of dead loads, but you've accounted for the internal stiffness. And that's really important for curved structures. And in Midas, that's the default for the deck as plate, beam as frame. Would use the, as it sounds like, deck as a plate, beam as frame. The all frame does the same thing. It's just using virtual transverse beams to model the lateral stiffness and the distribution of forces. And in Midas, you can also apply a 7th degree of freedom for warping effects. So here's kind of what that looks like. You'll see that I've kind of numbered my elements. This is a really highly recommended thing to do for mostly your output and manipulation. I typically try to do 10,000 series as girder 1, 20,000 series as girder 2. That way you can quickly go in and isolate those girders when you want to run it, your analysis out or look at moment diagrams, that sort of thing. Here you can see that this is basically the eccentric beam. You have this 10,000 element, 10,001, 10,002, and it's got an eccentric beam. It has the eccentric nodes that are rigid linked, and then the cross frames are fully modeled. And it also has that grid, so when you're trying to apply your live load distribution, it's creating an influence surface, and you're able to do that. And here it is in a 3D version. So what I'll be calling full 3D is going to be essentially an all-plate model. This is very similar, but the beam gets split up, or girder gets split up into plate elements for the flange and the web separately. That's again going to give you more accurate live load distribution, the same thing we talked about through the grillage, and the internal forces as well. But the biggest thing here is it's going to give you better rotational information. The flanges are going to be able to have more accurate localized stress distribution, and the flange is going to be able to rotate at the end more than it would for the web. And that's very important for curved girder design, to actually get those rotations right. And the only way to really do that is get into a full plate model. So this is what I mean when I'm saying three-dimensional. This is also for girders, specifically deep girders more than anything else. you get the effects of tension field action, which are critical for the design of those. We're using a relatively shallow girder for my design example that I'll be showing, so this doesn't have as much effect, but it's something that you should note when you're doing the design. Here's our model. One thing you will note there is we have a single web element that's covering the entire height of that web. So if you're trying to really analyze tension field action, you need to break that up a bit more. But for the purposes of what we're doing with relatively shallow girders, it should be pretty much fine, and we're not really seeing shear issues, so it was less of a concern. But what you can see is there's full plate elements for all of the deck, and you have these separated sides of your flange as a plate element on either side, and then the web as a plate as well. And then you have, just as before, the beam elements or truss elements for the cross frames, and this will model your lateral stiffness very accurately and also get the rotations of that beam. So in Midas, where do you go find this? In the composite girder wizard, which is very useful, you'll see that there's a modeling type, all frame, all plate, deck is plate, girder is frame. What they mean by frame here is beam element, is what I typically have called it, but you could call it frame or beam. And then deck and web is plate, flanges as frame. So again, they're going to do beam elements in this case for the flanges, and the web as a plate. I have not really used these ones as much. I usually do either all frame, deck is plate, girder is frame, or all plate. This one I have not explored as much, but it's going to be an intermediate method between some of these. So the all plate and the all frame are basically the worst boundaries that you could run. So I'll start to talk a little bit about our project here. This is CVG CONRAC, which probably doesn't mean much to most people. CVG is the CVG airport run by KCAB, which is the Kenton County Airport Board. And CONRAC, this is a rental car facility that they're putting in. So here's the Cincinnati airport, here's Cincinnati. This is the entrance into the airport as it exists today. Coming off the highway, coming down Terminal Drive. Terminal Drive sweeps around, comes here. It splits into an upper and lower level and comes through as a stacked roadway through the terminal and back out where it unstacks and then comes out. A little more detailed, again, you can see the split here with the gore down in this region. And then these have a grade separation, sweeps under, and goes through. So the final proposed condition, we will be adding a new garage at this location. This will be mainly rental cars so that when you come out of the terminal, you can simply walk to your rental car and go pick it up and take it right out. They also have another facility for that, and then there's parking garages. This portion of this parking garage was not highly used, and it was determined that that would be a very ideal situation is to go straight through and into this. So our project will be taking the terminal drive and realigning it directly into the airport. This is an MSE buildup, and the separation starts back here, then sweeps under and comes in as a stacked roadway through to the terminal drive. There's a number of other roadways involved with the project, but I'm not really going to talk much about them as they certainly don't need Midas modeling. So the structural components are essentially from this point, we have an MSE buildup up to here. And at this point, we go into our Unit 1, which is a straight rolled beam bridge. And the lower level roadway sweeps underneath at that point. There's a common pier with Unit 1 and Unit 2. And then Unit 2 is a single radius curve to Unit 3. All on piers. These are a single cap on 2 columns on drilled shafts, straddling the lower level road. In Unit 3, it switches to a pre-stressed I-beam bridge, which matches the existing structure coming into the terminal. This is a highly curved bridge. I've included the framing plan, although it's probably not terribly readable. But it is a 200-foot radius as the center line, minimum girder radius of 181 feet, degree of curvature and the delta are given here. But you can see it's quite curved. We actually had to use 2 reference chords in order to capture it because a single reference chord would not fit on any sheets. It is 8 spans, and they range from 48.5 feet to 68 feet in length. And all the cross frames and girders are radial. Everything in the structure is radial, which definitely simplifies analysis, design, and detailing. I'll go into a little bit of constructability guidelines and recommendations. So a lot of the reason why we had that many spans and they're shorter spans is due to geometric constraints. The access below, there's multiple access points coming in down here. You can't really see it on this site plan, but there are multiple access points that have to occur coming off of here at various points along the way. There's also geometric constraints that you should be aware of for your design of girders, and that's plate mill run. So usually whenever they go to make one of these, they're going to roll out a plate and then cut the section out of a plate. So what we ended up looking at is what is the plate availability in order to do that, particularly with such a high curvature that becomes very critical. In the guidelines for constructability by ASHTO and NSBA, that's a great guideline to look at, and it gives you this table that says, okay, if you're looking for a width of 96 inches and you have a 2-inch thick maximum plate, then here's your mill run length, your maximum length that you can readily get. So using that, we were able to just sketch that out, sketch the beam or girder into that plate, make sure that we're going to be able to order this thing as a single plate. They're not going to have to take additional plates and cut them up and weld them together. We'd like to get that as a single run for a field segment. We also looked at shop splices versus field splice. There's another table in that same guide that gives you, based on your thickness of plate, how much you would need to save in terms of pounds in order to make it economical to have a shop splice. This is for over your piers, having that thicker plate over the pier versus a thinner plate in your positive moment regions. And what we found is, at least in our structure, the shop splices really were not saving us any money, mainly because, doing that saves you money on the steel, but it adds labor. So the labor cost is too much to make that an economical solution. So we really didn't use much in the way of shop splices in this case, because we would have needed a 1/2 inch or 5/8 inch minimum differential, and we just weren't getting that in the actual field. You can interpolate, so this example, 16 inches, so if you came in here, you'd be looking at 80 pounds per inch as a savings needed for this 1.5 inch plate. If you're going from, a 1.5 to a 1 inch, you'd need 70 pounds per inch. That's kind of how to read that. And that pound per inch gets multiplied by the width of your flange. It's up here. So if it was a 16-inch plate times 80 pounds, you'd need savings of 1,280 pounds between the shop and the field splice in order to justify that, putting in that extra splice. And we just weren't getting there. It's a very useful guide. I highly recommend. This is our V-load analysis, or at least a portion thereof, originally. So we had predicted about an 11% increase in moments due to our curvature effects. And we designed for a 0.85 utility ratio. So basically kick that up to 15%. Really, we were getting somewhere between 5 and 11 down here in our actual analysis, depending on which span you talked about. But we went ahead for preliminary engineering and just kicked it up just to have it a little bit more conservative, and to account for the girder warping and secondary effects that aren't captured in V-load. Those are internal force effects that it's the limitation of the method. It's also estimated about a 5.5 kips for cross-ring forces. This is definitely an underestimate of what we ended up with. So do watch out for that in the V-load analysis. You probably will, particularly with high curvature, underestimate your cross-ring forces by that method. And again, this was used during preliminary engineering. We had originally sized these a little bit larger on the web. We were a bit conservative, and then we're able to take that down in our final analysis. We also separated from set single flange widths to having a larger bottom flange. Main reason there is that it's composite systems, so that's a little bit more efficient to do. But generally, our sections changed only a little bit in terms of overall area. Not a huge difference, which was good to see. So then we went to our, what I'll call again, the Grillage Plus, or the partial 3D model in Midas with beams as frame. And again, a couple tips for you as you're going through this. The node and beam element numbering is key. If you renumber those to make your life easier, it makes a huge difference. That's easy to do in Midas as well. We checked the geometry created by the wizard through CAD. So we just took a CAD, our normal base map, and then moved it in a scratch file to orient to the origin and angle that was coming out of the Midas output. And by doing that, we were able to go one-to-one between where a splice location was in CAD and where a splice location was in Midas. There is variation that occurs through the composite girder wizard. It's due to conversion that Midas is making. So whenever you run that wizard, it's converting all of your numbers into metric. It's then going to create the model, and then it's converting back into standard units. So because of that and some concatenation that's happening in the metric, there is some differential, but it's usually pretty small. And since finite element modeling is a approximate method anyway, it's not enough that we really felt like it makes a big difference. Also, the wizard is very, very useful and saves a lot of time. But just note that whenever you put that in and you output it, don't be surprised when there's, you know, some decimal differences between what you think it should be and what the Midas has, just because of that concatenation. One item for the curved structures is you want to make sure you're using local coordinates, and you do need to define a local angle at each node in order to do that. This is best done using Excel. So you can take the locations out of Midas and paste them directly into Excel, then using this equation that basically is just straight geometry, from the center point of the circle that you're basically working with, there's a delta y, delta x that are coming from the center point to the node of interest, and then using essentially that angle and then taking it and offsetting it 90 degrees, you'd get your local angle. It's a pretty easy thing to do in Excel. I definitely wouldn't recommend to try to do it by hand. And you can essentially copy out of Midas, paste that in, copy it down, paste it back into Midas. That gets all your local angles. And that really helps, again, with doing your analysis and making sure you're looking at it the right way. It also allows you to do, you know, similar kind of things between the geometry in Excel and a length along. So you can calculate from the nodes a length along the beam at each node. And that's really important when you're trying to take, say, stress regions or the shear stud locations and take them from the output into your plans. You really need to know that length along in order to get that. So you can calculate that using just simple geometry and Excel, but that's an important note as well. Bearing conditions and boundary conditions are a critical consideration. Make sure you're looking at those appropriately. And then by default, this is very important, Midas is performing a no-load fit analysis. And what that really means is that we have not provided additional camber or forced camber into the beam to make it plumb in the final condition. So when we put those beams out, as soon as we put them out, they're plumb, and then they're going to rotate as we put the deck or anything else on. You can do a final fit, erected fit condition, but you're going to have to apply a manual rotation in the model in order to do that. This is also typically not recommended for high curvature to do these methods. So the low load fit is typically the recommended, and essentially that's what Midas is doing. If you want to know more about this, I recommend the AISC presentation, Top 10 Changes in the ASH LRP code. This came out not too long ago, maybe a couple months ago. They also have these handouts available online. Please feel free to look at them. Definitely very much worth your time to do. One item of note for the camber as well, when you're determining the camber, if the radii is greater than 1,000, you don't need to account for it. I actually have this backwards. If it's less than 1,000 feet, you need to account for additional camber. Sorry about that. And essentially what this is saying is that during the placement, after you place the deck or during placement of the deck, there's going to be additional camber loss over time as the structure settles into its final shape and condition. And you have to account for this through these two equations that are coming out of AASHTO in order to do that. So just watch out for that. If you have anything with a radius less than 1,000, you need to add this extra camber consideration in. So Unit 2 modeling. We also looked at this through Leap Steel. Leap Steel now does both girder line and grillage, and actually now 3D full plate analysis as well. And we did run a LEAP model. And in this case, we ran a LEAP steel grillage and just compared the two. So a couple of things, and these are going to be more my personal opinion here. Some of them down below particularly, but LEAP does use STAAD Pro as its engine for analysis. Do be aware of that. So if you're looking at your licensing with Bentley, you need to make sure that you have both the LEAP and the STAAD Pro licenses. The main thing there is that the LEAP is serving as the GUI, but it's not giving you the actual full model to see unless you go hunt back through the directory. So when it's running the analysis, it'll show you the location. It's somewhere in the C program data, deep in the directory, and it's not easiest to find. You can get to it, you can find the model, you can open it, but you'll need STAAD to do that. So you just have to make sure you have both licenses. The LEAP model was faster to assemble and run than the Midas. However, the output is quite a bit, in my opinion, more difficult to use, at least currently. There's very limited data sorting and exclusion, and you're going to have a lot of data that's coming out of your models. And there's also limited capacity for visual representation, particularly for looking at your model as it's going into it. Again, you have to go back to that STAAD. You have very limited control over what nodes are connected where and how it's running that analysis. So you can see it, it's a bit, I don't know, it's a bit less visual and it's a bit harder to verify to me. And then when you pull things out of it, you get just masses of data, and it's a lot more difficult to use that way. But over time, I'm sure they're going to work on it as well. That's not to say that that's a bad program or anything. It does work just fine. It's just that I feel the GUI could use some work. So here's some comparisons between the different modeling types. We have our Midas grillage, our Midas all plate or full 3D, our MDASH and V-load, and our LEAP steel. And some items of note here, the Midas grillage, you can see underestimated slightly the deflections when compared to the all plate. The LEAP steel grillage overestimated slightly those same. And then the MDASH, the girder line, very much overestimated. However, at the end of the day, the actual absolute differences between these are not huge. The other thing here is that the final deflections here, 0.474, 589, 561, these are all fairly close, and we have our sacrificial haunch to make up for those. Also, for our MDASH, you know, if you did use this in your final cambers, again, the haunch would make up for it. It's not really going to be an issue, but we did see some pretty decent convergence and at least a fairly good range through a lot of our more advanced modeling, 377, 346, 313. That's pretty decent. So that's kind of that. Midas grillage versus Midas all plate. Again, this is the comparison. So here's your grillage. These are reactions. So these are deflections. These are reactions. In our overall comparison, there's some variation at individual locations and through individual loads. Overall, though, at the end of the day, we're within 1% to 2% of each other, which is very good. That means that our loads should be about equivalent. They might be getting distributed a little bit differently, but we've added the same loads. They are on the structure. It's a good verification check. And then our Midas grillage versus LEAP grillage moment and flange stresses. So at the end of the day, what it's going to use is a longitudinal moment stress plus the lateral moment stress, and it's going to determine that by the longitudinal moment plus 1/3 lateral. And we saw that there was some variation in the programs. Generally, though, at the end of the day, the utilization ratios coming out of each program were fairly close. Again, there are some variations, but at the end of the day, it gave us essentially the same answer. So whenever we were looking at what the required plate sizes were, we were getting about the same or within the 16th of each other as far as what they're recommended. So either way, we are getting the same sizes. There are, localized, deltas between these, though. However, so that's kind of summarized here. For reactions, the Midas grillage, Midas plate had very little difference. They also had small individual peer reaction differences. The Midas grillage versus LEAP grillage differed in some of the reaction distributions. So that had up to about a 10% difference in the distribution of reactions at a pier between what each girder was seeing. Again, these are approximate methods, so you can't really necessarily say one is more right than another. You could get a little more detailed in the analysis. But overall, we're seeing a general convergence on our design. And then the Midas grillage versus the MDASH girder line shows a larger difference in deflections. Again, that's why we're doing this more detailed analyses, is that the girder line is not sufficient to accurately predict our deflections. So moment comparisons between the grillage and all plate are not readily available. When you take an all plate output, what you will see there is just stresses. You're not going to see moments. So that's an important note. So whenever you want to do that comparison, you need to do a conversion between the grillage model moments and get that into stress to actually do a comparison. In the LEAP grillage and the Midas grillage, they provide similar stress outputs and required plate sizes. You know, again, the utility varied. Program interpretations did play into this. Lateral bracing was one of the ones that we identified, where you're explicitly telling Midas what the lateral bracing should be for each member for that length. In LEAP, it doesn't do as explicit an application, and we saw some variation in the capacities due to that, which changed that equation. So there were other parameters as well that had some effect on that. And in general, LEAP provided a higher lateral bending stress, but very similar overall combined stress, which is what it's really using for the final design. So takeaways of this, the girder line analysis overestimated deflections substantially in the final condition. Again, substantially, I'm just saying as a % increase, not necessarily a overall amount of inches increase. The girder line analysis underestimated the initial stage. The LEAP slightly overestimated deflections versus the all plate. Midas grillage underestimated versus the all plate, again, slightly. It's very important there. And then in general, everything was coming within about an 1/8 inch of each other on our more advanced analysis. And given that our sacrificial haunch, which is on top of the beam, is 2 inches thick to make up for the variation, and we have a 1/16 inch tolerance in steel and an 1/8 inch tolerance in concrete, an 1/8 inch is going to just get sucked up in the tolerances that we're already working with. And we have that haunch there specifically to make up for these variations. So any variation that we're seeing in that range really should not be an issue in this case in particular. On deeper girders, this may be more substantial. So this is a fairly shallow girder at 33-inch web plate. For bigger girders that may be 60-inch or big deep girders, this could become much larger, and you're going to need to look at that a little bit harder. And the Midas grillage provided similar actions to all plate. And again, one of the items too, when the all plate comes out, it does not allow you to do a code check at this time. So you can definitely use it for double checking your stresses in your beams, your rotations, your deflections. But when you're getting to your code checks, you really need to have the more grillage model in order to do that. One code commentary that we ran into, this is for the flange lateral stress. So in the design of the flanges, it says you don't want to exceed 0.6 FY or 30 KSI for a 50 KSI beam. And normal check equation is the FBU plus 1/3 times FL. What we were seeing in a number of cases when we originally ran this was that this FL was higher than this limit, but the overall FBU plus 1/3 FL was lower than our required. So we were okay overall, but we were exceeding this provision. And going into the commentary of AASHTO, it has a somewhat annoying definition as far as this goes. And what it's really saying is that in cases where it's computed elastically and that the stress is larger than 0.6 FY, the reduction in major axis bending tends to be greater than that, determined based on these provisions. Service and strength limit state provisions of these specifications are sufficient to ensure acceptable performance of I-girders with elastically computed values, and this is the annoying part, somewhat larger than this limit. And they really don't define this at all in the code or the commentary. So in our judgment, we just said if we exceeded this 30 KSI by 10 to 20%, but we're well below our final utility ratio. We are comfortable with that. This becomes a bit of an engineer's judgment, and again, that's something I may look to AASHTO to hopefully clarify sometime in the future. Boundary conditions, again, are important here. What happens with your thermal is very, very important for a curved bridge. In our case, we chose to fix this point as our true point of fixity on the structure. This is girder line 3, and it's at the central pier. And what you'll see here, this is a diagram from our plans showing which bearings are oriented which direction. We have freed, any of the circles are freed. Anything that has these lines are fixed in a single direction, and this is fixed in all directions. So girder line 3 was our controlling girder line. You can see that transversely, we have put in retainers on either side. These are steel retainers to keep that in line with where we want it to go. We did allow some delta, I believe it's about a ½ inch between the girder set and actually engaging the retainer. You can do this a number of different ways, which I'll get to in a moment. But these are essentially fixed transversely and free longitudinally. These are all free, so this is going to be the controlling, and these generally just float from here. At this point, you can see that these ones have a longitudinal restraint. On either side, this will be the fixed pier. So we've not let that move longitudinally. This is using a slotted hole and anchors in order to achieve that. So transversely, we're allowing movement, but longitudinally, we are not. And you essentially just don't want to lock anything up, or if you do lock things up, you need to take that in force. So you either take it in movement or you take it in force. And with the curved girders, they're really going to try to either open or close, concave or convex, when they see large thermal deltas. So that's just an important note to look at. You also need to make sure that whatever you're allowing in terms of movement here at the end is compatible with what expansion joint you're moving, both in the longitudinal direction and transversely. And if you're using something like a finger joint, usually the transverse movement is highly limited. In our case, we were able to get away with a more strip seal joint, and those provided a lot more movement capacity in both transverse and longitudinal. But you get to a very long structure and you need a finger joint or something modular, do watch out for that, because transverse could become a big problem there. Here it is from the model. You can see that there is a component on every one of them. That's because we actually put in the stiffness of every bearing. So just through the shear modulus, there is some small amount of thermal reaction. But the big thing is you're getting most of your longitudinal reactions at your fixed pier. And then most of and it's harder to see here, I probably could have taken a better sniff of that, but most of your transverse is occurring along girder line 3. So that takes us through most of the final modeling. So we'll get into construction sequencing and deck pours. Normally we would pour the ends first, then positive moment regions, then negative moment regions. And the reason for this is you want to prevent cracking in the negative moment region or loss of concrete in the negative moment region during that positive moment pour. So, when you pour the positive moment on two sides of a pier, you're going to get strain over the pier, which would separate that deck pour or pull apart a previous deck pour that you don't want to have happen, particularly in the early stages of the concrete setup. So that's really why we care about that. In this case, though, with as short as our spans were, our reversal regions were so close to each other that it really didn't make sense to do that. So instead, we're going to pour the ends to hold down the structure and then work our way towards the middle. And we're going to pour positive and negative moment regions together and up to contrafracture points in order to minimize some of that effect of the next pour sequence. And we're not really seeing a huge delta from that, which is good. So during the construction sequencing of the deck pours, you do have to worry about several different forms of distortion. And this comes from the connectivity between the beams and girders, cross frames or diaphragms, whatever you're using. And particularly for curved structures, you're going to see a lot of this. And it can result in a few different things. The worst thing that you could ever happen is, of course, the girder rolling and falling off, which hopefully never does. But even if it doesn't, just having some local distortion here and having this beam rotate out, you'll get some deck loss above the beam because of that angle. And that's kind of a problem. So we want to limit that as much as we can during that pore sequencing. So there's three primary sources. These are all stolen from the ODOT Bridge Design Manual. Global superstructure distortion, this is your differential deflection between beams. So the deflection of an exterior may be different from that of the interior. Because you have a differential deflection, there's a rotation inherent in that because you have the cross frames holding it up. Oil canning, that's basically a localized web deformation in the lateral direction. And this one, we haven't really explicitly modeled in what we're doing currently. If you got into a deeper plate girder, this could become critical, and you're going to need multiple web plate elements in order to accurately model that. And then you're going to need to apply this bracket load at that point in order to get that modeling in there. We are currently not addressing that as explicitly in the Midas model, as I'll show you. And the third is girder warping. And this is just the torsion between cross frames. So these are your brace points. And because you have a bracket out here and you're twisting it, there's going to be distortion in between the lateral bracing. And this is the most explicitly modeled within Midas that we are doing. There's also screed loads, which is from the screed machine that sits on that as well. For straight bridges, you often calculate this using torsional analysis of exterior girders. At least that's what I use. TAG is kind of a common name for it. This was developed by Kansas DOT. It's freeware. It can be downloaded at this website. And it will do all of these analyses for girder warping, for the oil canning, and for the superstructure distortion as a straight girder line for you. And it's a pretty quick thing to run. In our case, though, we're using Midas to do this for cases 1 and 3. Basically, the girder warping from this and then the superstructure distortion, because we already have these. The deflections are in there in our model for this distortion, and the deflections and rotations are in there as well, as long as we add the loads for this case. Note, too, that a lot of this has to do with the plate elements, the localized plate elements here, and what's happening in the localized stresses. So that's very important, and that's a reason why the plate modeling is much more accurate for rotations, is this localized rotation within this section, as opposed to seeing this as one piece with flanges and the web all together as a single unit. All right, future Midas development may include, this would be something for our Midas friends, moving loads during construction staging for the screed loads would be wonderful. However, you can do this manually right now. Typically, I'm looking at that over the piers and over positive moment regions, the worst case locations, wherever you have the worst case positive moment, worst case negative moment during construction, probably going to be your most critical for your screed loads. Alternatively, and this is what we did here, we analyzed all the loads except the screed machine in Midas, and then used the stress outputs of that into TAG, and then just ran the screed and oil canning as a very localized effect that's happening to just model that and analyze it. And we're well below our limitations. So because we were so much lower, we didn't feel that there's any need to go try to model that more explicitly. And then the all-plate model used the construction sequencing and dead load verification. So this is big for, again, that deflections and rotations. So here's kind of what the model looks like. Start off with the end pores, hold down those ends. So after that's in, all subsequent rotations are going to be less because we provided that hold down. Here's the next pore. You can see that it does go over a couple piers. But what looked like a reasonable amount, we're also making sure that we're symmetric in our pore sequencing. There's the pore number 3, and there's pore number 4. Loading of these. So in the Grillage model, we used vertical distributed line loads with an eccentricity. This is the easiest way to do that. So here you have a walkway, you have your wet concrete, you have a construction live load on the top, and then a screed load. And these can be applied, these are mostly pressure loads, and they can be applied using an eccentric line load. So you just take the weight, the 50 PSF or whatever it ends up being, multiplied by that width, and then offset it out where it needs to be. That's an easy way of doing it. It gets the moment, distributed moment that's part of that, all inherent in one input, which is kind of nice. It's pretty quick, pretty easy. In the plate model, you have to do a little extra work. It's not going to let you do an eccentric line load, and it will not let you do a distributed moment. Other programs, I have not seen this either. Mostly in plate models, you're going to see nodal loads or just plate pressure loads, which are a bit annoying to use because you have to calculate based on the length of that element, what that nodal load would be, and if all of your elements are not the same length, that becomes a bit of a challenge. However, in Midas, they have put in a provision for what's called edge loading on your plate. So we're able to do a line load on the edge. That's actually a big time saver and very useful here. The one thing, though, is that you can't get that eccentricity and you can't get the moment generated from it. So how do we deal with that? Well, we looked at it and we said, okay, if this line load had an eccentricity, that creates a line moment. And if we take that line moment and divide by the height of our web, we can decompose that line moment into a force couple. So what we have is a line force couple at the top and bottom of the web in order to account for the bracket loads and those eccentricities. And so that's how we modeled that, and it definitely made it a lot easier again than trying to apply individual nodal moments or nodal loads. And then the grillage versus the plate, the end result of this. So the general rule on rotation limitation is about an 1/8 inch per foot. This is kind of a rule of thumb. Some of the DOTs have adopted it in their bridge manuals, but it's not really a code provision. It's not from AASHTO. It's just a judgment call that they're making. So we looked into this, and I guess this is just more note for your output. Use the local rotation. So again, you need that local axis defined, and then current step displacement is the current step of that pore. The other way is that it's going to try to do, if you don't check this on, is the overall total plate displacement, which is a sum of multiple steps, and that's not really what you're looking for. You're looking for what's happening during that pore. The worst case is during the first end pore. Once we have those ends nailed down, the subsequent pores are better. And the all plate is a bit more accurate for this, and it provided, as you can see over here, much higher rotations. The deflections, vertical deflections, were very similar, but the rotations, the twist of the girders, was much, much higher in the all plate. And it was above this 1/8 inch per foot. So we looked at this and we said, okay, what can we do with this? Well, we went in and we said, okay, as a short girder, not very tall, that rotation results in a much smaller deck loss than if it was a very deep girder. So it's a deep section. That rotation of an 1/8 inch per foot at the top multiplied by the height of your girder is a much larger end value than what we're really dealing with. So we went up to a 1/4 inch a foot as what we were comfortable with using in this case, and we were within this limit everywhere. And then we also went in and said, you know, just as an end case on that, we'll also provide temporary timber blocking at 1/2 the cross frame spacing within the region where the deck is being poured. So wherever they're pouring it, where we're getting the larger rotations, we're going to have them put in extra timber blocking, and that's just to make sure that we're not going to see any major issues. And again, the overall total, if you're using a 60-inch deep web, you know, 60 inches here times this, you're going to get a value that's very similar at the 1/8 inch to what we would use at our 33-inch times a 1/4. So we didn't feel that the overall would needed to necessarily meet this provision just because we are a shorter girder, and we did provide the extra, you know, timber blocking to account for it. So that's the end of the CONRAC and the models. I'm going to go very quickly through because I know we're running a little bit later on time. The other project that I have here, Guernsey 513 for ODOT. This is District 5, and run through that quickly. So SR 513, this is State Route 513, this is I-70, and we're working on this interchange here. It is both a horizontally curved and a vertically curved large sag curve coming through here. This kind of comes up a mountain, or mountain as much as we ever have a mountain in Ohio, but big hill, put it that way. And it's a 4-span, 60-foot, 2 at 86.9, and a 60-foot 10. As far as spans go, skewed. So this is skew is to the reference chord. It's not a radial skew. So it's a little bit more complex geometrically, but it does have a much larger radius. And you can see the radius of the center line is 1206, minimum girder radius is 1185. So much larger radius, but with a skew involved. There's a degree of curvature, delta. The cross streams and the girders are radial, even if the skew is not, and it's on the vertical side. So this also had part width construction, including pure cap part width construction, and that was a bit more of the challenge with this as well. There you can see the framing plan. It's a bit wider. We've got our closure pore in the middle. Here you can see the skews and the curvature. One item note, this is not structural, but we had horse and buggies, Amish horse and buggies going across this bridge, as well as a lot of truck traffic and semi-traffic. So we ended up having to do a single lane signalized when we had to account for both heavy semi-trucks and these guys. So our ramp queue and red time clear analysis for our traffic engineering had to account for that fact, which was a bit of a challenge here. Again, not really structural, not related to this, but I find it interesting. So Midas was used for design. We did our girder line with V-load analysis for the preliminary. There was no change in size. So again, we were up in that above 1,000-foot radii, and we did not really see much of an increase between the V-load and the Midas. But again, it's a much larger radius than CONRAC. So over 1,000 feet, V-load seems to be pretty good at predicting. We did a separate Midas model for temporary support analysis and design, for the phase construction. And here are some notes about doing a temporary shoring in this. So you need to make sure that you're including the relative stiffness of your concrete column versus a steel temporary support. So if you're using steel for support and it's a concrete column, there's a difference in stiffness there. And you really need to make sure that you're accounting for that in your design. In our case, we used a full moment of inertia for the column. That was mainly due to the fact that the column remained in compression. If your moment is big enough to pull a side of that column into tension, you probably need to be using a cracked moment of inertia in order to do that for elastic analysis. But if you have the compression enough that it's not really going to crack, you can use that full section. So the biggest thing for Midas design analysis that was very useful for this was we could output design results of the composite beam, the concrete column, and the steel temporary support using the three different methodologies of the composite, concrete, and steel, all from the same model file. Did not have to have separate model files, could use all of those separate codes at the same time, well, same code, but separate chapters of the code at the same time. In this case, we used extensions of the footings to support the temporary support. So relative stiffness of the foundation is not necessarily needed here. But if your temporary shoring is on matting or it's on a separated footing, or you have say a deep footing on piles that's supporting your overall pier, and then you have a shallow foundation on a spread footing that's supporting your temporary support, the relative stiffness between those foundation units could become a concern. Again, though, we attached, so it was not an issue here. It is possible to do that, though, in Midas using spring assignments at the foundations. You could put springs under some plates for either the timber matting or for a spread footing that you poured, and you could model that in there. And then we need to provide room for adjustment during construction. This is really important anytime you're doing anything temporary shoring. So in our case, we made sure that we provided hydraulic jacks at the top of our header beam underneath the pier cap. And the reason for that is we want to make sure that we're providing a positive contact, to make sure that we're fully engaged with that pier cap. So you can't really do that terribly well if you're just going to make them try to shim everything. So I definitely recommend hydraulic jacks. And then we've also provided grout under the base plates. We're on top of an existing footing. You don't know if that footing is level. So you need to provide, a provision to get that level and set where it needs to be. So here's our complete phase of the model. So this is during the first phase of construction. We have our, pieces of our concrete pier here, and we have these temporary towers underneath. And then we've got our full deck pour, and there will be live load traffic on this as well. So using the Midas, it will also do the live load on this. Here's what this looks like in plan view. You have basically a leveling pad and base plate coming up into a tower. And then you've got these cross members and bracing, and then goes up to a header and transfer beams that are taking it. And then here's the hydraulic jacks underneath, again, to provide that positive contact with the pier cap. And we have added this extension that's doweled into the existing footing in order to provide a solid unit here to support this. So there's a model with just the pier and the temporary shoring. Here it is in the first beam setting. So here we've got the beam setting. Really, this would probably get poured with the deck, but we wanted to include that a little bit for the staging. It's a little easier to do that as a grouping with the rest of the cross frames. You could separate it though. And then here is a screed load. So we manually applied screed loads on this one. This is for the positive moment region. And we put these screed loads out here as eccentric nodal loads in order to analyze that. We also did it at the piers, but this is the positive moment case. And here it is with the deck on. So in conclusions, Midas capabilities for construction staging and ability to analyze, design multiple stages, as well as multiple material types within a single model is very advantageous. I've done this in the past where you had to have a separated save off each individual stage of construction and analyze it separately. That's a big pain. The other thing too is doing the temporary shoring model instead of having a separated, say, leap concrete for the pier cap, and then you go into a different either STAD or some other hand calculation for the steel. Having it all in the one, it can output all of those design results out of a single model is very, very useful. And proper analysis of construction cases is becoming a key aspect, or it's always been a key aspect of bridge engineering, but we're expected to do a lot more, I feel like, than we have in the past. And so I don't think that's going to get less. I think we're only going to see more of that in the future, unfortunately, due to failures or issues that have happened in the industry. AISC and SBA have a lot of those guides for constructability. I really highly recommend them when you're looking at a project like this if you're not familiar. They are definitely useful in letting you know what you can do, what your limitations are, just to make sure that it's constructible, it's biddable, it's not going to be a problem to fabricate. V-load and girder line, accurate for larger girder radii, but become less so for small radii. No surprise there. You need to provide contingency for girder warping, internal force effects. Again, that 1,000-foot, 1,200-foot is pretty good cutoff for looking at that as to whether you need to provide a lot of extra or if it's going to be pretty close. Midas Grillage, Leap Grillage provided similar results overall. There are some variation in the details of those results. We probably could get it down to a little bit less variation if we spent more time with it, but we felt pretty good about where we were, particularly with having 3 different advanced models and our V-load. That's a lot of modeling, so felt pretty decent about it. But we probably could get those differences down if we dug into the models a bit more and really tried to get them dead on exactly the same. The Grillage Plus Limited 3D provides good results for design of girders, final condition, and forces during construction. But the big thing is this grillage is going to underestimate your girder rotation. So you still really need to do your all-plate model when you're looking at tight radii to make sure that you can verify what that true girder rotation is during the deck pour sequence. And the best practice for the fine element, which is what we did here, independent models by independent designers. So the LEAP model was done by a different person than the Midas models. And then they had a common checker and a common final reviewer. And there was cross-review by the 2 designers of each other's model. So having those 2 independent models converge and they're done by different people, that's really important, and I think provides a very good cross-check that we're reasonable. And that's partly where some of those differences come from as well, because when you have a different designer doing it, they may set up the loads a little differently, that kind of thing. Some of the properties, to use an N of 7, 7.5, or 8, that kind of thing can change your composite stiffness slightly, which changes your distribution. So there's a little bit of that just to be expected. And then special thanks to the following people. Paige Sechrist did a lot of the modeling with Midas. Pat Flues did the Leap Grillage, and Mike Avellano and Ron Maddox provided review on these projects, and thank you to all of them. I'm now able to take any questions, and I think we're not too bad on time, maybe right at 4 o'clock here. So if there are any questions, I'll be happy to answer.
All right. Thank you, Mr. Les. I have some questions ready from the engineer. So if I know our time is almost is up, but if you could answer them briefly, that'll be great.
Okay, sure. So what is the advantage of a 2D model with the deck model concentrically using plate elements and the cross frames fully modeled versus going to 3D model? So there's two things there. The 2D with the plate elements is going to allow you to get explicit design checks, code checks out of it. That full 3D all plate, you cannot get code checks out of. That's a big pain to go through, and then you'd have to manually calculate all your own code checks at each point of interest. The 3D model also takes a lot longer to run. So in terms of run times, moving from the all frame to the all plate, as you add more plates in there, either the deck or the web, you're increasing your run times. So I would say run times and then the explicit code checks are probably the two biggest things there. You mentioned being able to better address tension field actions. Some 3D models, Midas performing some kind of non-linear analysis is directly capturing post-buckling effects. Yes, so this one, in our case, no, we did not include that. We have a fairly shallow girder that we were not horribly concerned about that. However, Midas can perform that nonlinear analysis for you. You would need to add a lot more plates into your web in order to do that. And you would need to turn on the functionality of the nonlinear analysis. So no for my model, but yes, it can be done. And how long is the computational time for LEAP 3D and Midas 3D? So the LEAP full 3D, we were not actually able to get to function. There was an issue in the program. They have since released a patch, and I have not actually gone and tried to have it create the 3D model as yet. But there were issues where it was not creating the supports as it should have been, and it was crashing. So I can only talk to the LEAP Grillage. And the LEAP Grillage was a little bit shorter time frame for runs than the Midas Grillage, depending on how you set it up. It's going to allow you in the LEAP Grillage to choose your step increment for the live load analysis, and that had a huge difference on the run time. So if you had, 2 feet increments between where the live load could be placed versus if you had, 6 inches between where they could be placed, you would see a vast difference in the runtime. So it kind of depended as far as that goes. The Midas Grillage typically was running at maybe 10-15 minutes. The LEAP could vary anywhere from 10 minutes to half hour or hour, depending on what that step was. So it could really vary a lot. So I would say that there is some computational time difference, but not a huge amount, and it's really going to depend on what your input is. And again, I can't really speak to the LEAP 3D as yet. I believe they did just release the patch that will allow that to work. The Grillage and the line girder out of LEAP don't take terribly long, though. You just got to watch that time step or live load step. If only use Midas to do model design, how do you check to make sure the results are reasonable and the model is correct? Oh, this is a big one. So I would tend to not do only a Midas model. You really want to have some other backup. And that's mainly, and this is not explicit to Midas here, this is for any finite element modeling that you do. It's an approximate method. So you really want to verify that. And I would do that by at least doing a girder line analysis with, if it's curved, a V-load. But at minimum, I would try to do girder line to make sure that you've got some other basis to say, is that in the ballpark of where you think it should be? Girder lines don't take long, the V-load doesn't take long. At minimum, do that. You don't necessarily have to do what we've done here with these extra finite element models. I'd say that's a best practice, but of course, we don't always get the fee to do that kind of modeling. And as fees go down and we're trying to be more efficient, you might see that you couldn't really do that full thing, but at least get that girder line in there. You definitely don't want to use just a finite element model. So hopefully that answers those questions. Are there any others?
Actually, there are other questions, but I know that our time is up, so I think we're gonna have to let you go, Mr. Les. And for any further questions that you have, please send it over to us, and we will happily answer for you guys. Yes, that. Thank you very much, Mr. Les, for your presentation, and I think this will be the end of our webinar for today.
Okay, thank you very much for all the attendees. Appreciate taking the time.
All right, thank you, everyone. Goodbye.